Scalable Methods for 8-Bit Training of Neural Networks, work by the Technion Israel Institute of Technology and Intel AI. Deep neural networks achieve remarkable results in many fields. However, as these networks get deeper, using neural networks and training them can be highly inefficient. Low precision, or quantized neural networks, have the potential to reduce computation time drastically. It has been shown that 16-bit is a sufficient precision for most network training, but further quantization, i.e. 8-bit, results with severe degradation. On the other hand, for inference, 8-bit has been shown to be sufficient, implying that the problem stems from the gradients. Since the gradients are involved in 2/3 of the training computation, quantizing the gradients is a critical step towards faster training machines. When is quantization of neural networks possible? To answer this question, we must examine quantized neural network deviations from full precision neural networks. Since the output of the batch norm layer is known to be invariant to the norm of the weight on the preceding layer, the only measure that needs to be preserved is the directionality of the weight tensor. In this work, we find a lower bound which indicates that with m-bit fixed point representation, angle is preserved when the number of quantization levels 2 to the power of m is much larger than square root of 2 times natural logarithm of n, where n is the size of quantized vector. We note that this result heavily relies on values being distributed according to a Gaussian distribution. To validate our assumptions, we ran a set of experiments on CFAR10 dataset, each with a different number of bits, and then plotted the average angle and the final accuracy. As can be seen, there is a high correlation between the two. Additionally, the following observation can be made. 1. During quantization, the direction of the vectors is better preserved with the forward pass compared to the backward pass. 2. Validation accuracy follows tightly the cosine of the angle in the backward pass, indicating gradient quantization as the primary bottleneck. And 3. As expected, the bound holds in the forward pass, but less so in the backward pass, where the Gaussian assumption tends to break. Given an upstream gradient GL from layer L, layer L-1 needs to apply two different matrix multiplications, one for the layer gradient GL-1 and the other for the weight gradient GW, which are needed for the update rule. Our analysis indicates that the statistics of the gradient GL violate the quantization assumptions. Thus, quantizing these gradients constitutes the main cause of degradation in performance. Accordingly, we suggest to use two versions of layer gradients GL, one with the low precision and another with the high precision. As the gradients GW are required only for the weight update, they can be computed in parallel in most cases with high precision, while using low precision GL required for the backwards stream. Vanilla batch norm implementation requires the computation of the sum of squares, square root, and reciprocal operations. These require high precision to avoid zero variance and allow a large dynamic range. Previous attempts to train low precision networks did not use batch normalization layers or kept them in full precision. We suggest range batch-norm, a layer that normalizes according to the range of the input distribution, making it more tolerant to quantization. For a layer with d-dimensional input, range batch-norm normalizes each dimension according to its dynamic range, where Cn is the scale adjustment needed to approximate the vanilla batch-norm standard deviation. We ran experiments with ResNet18 and Res50 on ImageNet dataset, showing the equivalence between the standard batch norm and range batch norm in terms of accuracy. Additional experiments using a transformer model further validate our conclusions. To summarize, in this work, we present guidelines for quantization of neural networks. We show that directionality is well preserved during quantization when the tensor is Gaussian. We argue that since the layer gradients are non-Gaussian, they fail to preserve direction, thus harm quantized neural networks accuracy. And to solve this problem, we suggest quantized backpropagation, which maintains two copies of layer gradients, 8 bits and 16 bits, and range batch norm, which is a viable normalization alternative for low precision. This work demonstrates for the first time that 8-bit training on large datasets is possible in all computational bottlenecks with little to no harm in final accuracy.